let's start with any questions. Do you guys have any questions on anything that we've done to this point? Homework questions or anything else? Sometime after I've graded them, which hasn't happened quite yet. So hopefully I can do that today. That's my hope. Nathan? Nope. Lucas? 21? Yeah. Hey, Crinkles, what did we say about this? Start bringing a paper plate, and you guys can all just do a buffet at the start of class. You can all get all your crinkling done, throw everything away, and then you just have a little bit of everybody's snack or whatever. All right. So, Lucas, you had wanted to do 21, which we're deciding whether these things are odd or even. So I'm just going to go ahead and start by looking at the graph so that I know whether I'm looking for something that's odd or even. It's much easier to try to prove something if I can tell what's going on. If I look at the graph, I notice that the first quadrant and the third quadrant looks like reflections of each other. That's exactly what I expect to see from something that's odd. So that's what I'm going to be trying to show. So to show something as odd, what I need to show is g of negative x is equal to negative g of x. So if I do g of negative x, it means I'm just going to be plugging negative x in for x. And I know that the negative, if I have a negative inside the fraction, I could put that negative in the numerator, the denominator, or just out front of the fraction, which is where I'm going to put it. Cool with that. And this part right here is just my g of x again. So I'm done because I've shown that g of negative x is equal to negative g of x. And that's it. You just have to remember that fact about the negative sign in a fraction, that you can kind of move that around wherever you want. But that'll do. Anybody else? There's no reason this can't be fun, guys. Okay? All right. Let's go ahead and finish up 1.7. So we're going to start and finish 1.7 today.
What? Where is it? Right there. So you Kill it. Kill it. You got it. You got it. You got that. You're going to slash it. You got it. Sorry. You got it.
It's just a bug. It's fine.
I really like it.
More than just a bug.
All right. 1.7 is the last section that we're doing in Chapter 1. What does that mean that's coming soon?
Is it a week from yesterday?
A test. So we're going to finish 1.7 today. We'll plan on doing the review on the next class, and then we'll be testing beginning of next week. Yeah. Okay? So just as a heads up on that, I think that's all up in my Notre Dame, the dates on all those things, at least to the best of my knowledge, or that's the plan right now, obviously subject to change. Could the test ever move forward? No. Once we pick a test date, I'm never going to move anything forward. We may move things back, but we won't move things forward on you. Okay? So it's always, when I give you a best guess, it'll be the, like the earliest something could be done. You get what I mean? Okay.
I got you.
Because boy, that's pretty rough to get the reverse, right? It's like, oh, I was expecting the test on Monday. It's going to be Thursday instead. Like, yeah, that's a mean trick.
I mean, if you moved it back, it wouldn't be.
Yeah, exactly. That's in general. That's my method. Is I will pick the earliest date something could be done, and if it doesn't look like that's going to be a good idea, we can always move back, and nobody usually gets upset by that. All right. So 1.7, we're going to be talking about function operations. So let's start by just defining our basic 4 function operations. So let's say let f and g be functions with intersecting domains. Then for all values of x in the domain, and maybe I should say the codomain, the domain in common to both functions. We can say the sum of 2 functions we can compute by just doing f of x plus g of x. And the difference of 2 functions just would be f of x minus g of x. The product of 2 functions would be f of x times g of x. And the quotient of 2 functions would be f of x divided by g of x, provided that g of x is non-zero. So I think all of that is working just the way we would hope things would work. Let's just do a quick couple of examples on what's going on here, and then we'll keep on inching our way forward here. So let's say we have 2 functions, f of x, which is 2x minus 3, and g of x, which is square root of x plus 2. And we're asked to do f plus g of x. Well, from our definition above, I know I can just write that as f of x plus g of x. Yeah, and I know f of x is 2x plus 3, and g of x is square root of x plus 2. Bless you. Now, once we've done that, all that would remain is to simplify what we have there. So to simplify something like this, all I really want to do is combine like terms. Is there any like terms to combine here? What do you guys think? I see you, Boyd. I'm going to get to you in just 1 second. I want to finish this thought, though. There's no like terms here. You can't add things under the square root with things not under the square root. And you can't add x's and constants. So this is just as good as it can go. That's all you can do. Boyd, question?
Yeah, so it says 2x minus 3 and...
Oh, did I write? Yep,
Oh.
I just wrote the wrong thing there. Thank you very much. And we'll write that in blue so people can see that I changed that. Yep, you caught me. Thank you very much. Paying attention, I like it. All right, let's do some more examples, just kind of the same sort of stuff. Although Mr. Kulik's going to try to trick you with algebra here. So what if we want to do g minus f of x? Well, if I use my definition above, I can just write g of x minus f of x, right? And if I plug in what those things are, that's square root of x plus 2 minus 2x minus 3. Everybody agree with that? I fooled you all. That is incorrect.
Well, no, it doesn't have to be first.
No, they're just letters. Like, they're just names of stuff. There is a mistake here, though. There's something wrong with what we've written.
Second part.
What? Okay. Plus or minus?
He's gonna have to change to a positive.
Yeah, so the f of x, the entire f of x needs to be subtracted. So really that negative, that subtraction symbol needs to apply to both parts of f of x. Yeah, so what I really want to write this as is negative 2x plus 3. Ah! You caught me, Mr. Kulik. Did you guys see what happened there? Super common mistake to not want to put those parentheses in. Why do you think I'm showing you this example? So that you hopefully catch this next time when you're doing it on your own, right? This is something very common to happen. Students make this mistake a lot. I'm pointing it out to you and making a big deal of it so that hopefully it sticks and you're on the lookout for this kind of a mistake when you're doing your own work. Everybody cool with why the negative became positive there? Alrighty then. So we have g times g of x. So again, if we just use our definition from up above, that's just g of x times g of x. And we know that g of x is the square root of x plus 2. So we'll just plug those in. Now what?
Could you put the squared?
Yeah, so I think what Nathan is saying is since I have x square root of x plus 2 times square root of x plus 2, that's the square root of x plus 2 squared. Right? Is that what you were getting at?
Yes.
Okay. I agree with that. What else could you do there? There's still something else. Yeah, the squared and square root cancel. So we're just going to end up with x plus 2. Everybody so far so good? No biggie so far, right? Just a little bit of algebra. If I have f divided by g of x, again, using our definition above, we can rewrite that as f of x divided by g of x. And we can plug those values in. And what do we see there? Anything we can do with that? Whoa. It feels like I'm looking for an answer here.
I don't know what the answer is.
Okay.
The square root.
Yeah, what about the square root?
Doesn't it have to be above? Above?
Yeah, so Sophia's right on. Way back in geometry class, you'd said that
Way back.
things like 1 over the square root of 2, we were never going to write that way. We're going to do like multiplying by the conjugate so that we can write it without the radical in the denominator. You guys remember doing that?
Oh, yeah. It looks like that's what we want to do.
So it's certainly we could do that here, but what is really the difference between 1 over the square root of 2 and square root of 2 over 2?
The square root is the top.
Nothing.
There's, other than the way they look, there's no difference, right? If I type those into my calculator, they're the exact same decimal. Everybody agree?
Yeah.
So all we're talking about is the way something looks, right? So it's really a matter of preference whether we need to do this or not. So here's the preference that I'm going to give you guys, the one that we're going to work with, is when your radical is in the denominator is just a number, we are going to rationalize the denominator. Maybe we'll do this. When the radical in your denominator involves a variable, we're just going to say that's good enough. So you notice how the radical in my denominator that has an x under it also. In those cases, we can just, I'll say that it's fine to just leave it the way it is. If you went ahead and multiplied the top and bottom by the square root of x plus 2, and you wrote your answer as this, that's what it would look like if you did that correctly. That's fine with me too. It's not wrong if you do it. I just would say I'm not requiring you to do it if there's a variable in the denominator. Okay? Everybody feel that seemed fair enough? So anything that you would have rationalized in geometry class, let's continue to do that. Anything that's got like kind of a weirdo variable in the denominator with the radical, like you just leave that be. What do you think?
Sounds good. Makes sense.
Yeah, it's all right. All right, so we've talked about the 4 fundamental operations for functions: addition, subtraction, multiplication, division. There's actually a 5th one that ordinarily you would talk about in your Algebra 2 class, but I don't think you guys got there.
If Mr. Conley,
Yes, he has a new job. I know. I'm sad too.
where'd he go?
He's working at he's doing like accounting work for a trucking company, I think. All right. So let's talk about this 5th type of operation. So let f and g be functions such that the domain of f intersects with the range of g. Then we define the composition of f and g as f composed g of x is equal to f of g of x. So this new operation that we're learning about here right now is called composition. And I want to talk about this series of symbols right here. Yes, Nathan.
What's in between them?
Huh?
What do we put in between them?
So that's like the multiplication dot, but instead of being closed,
Oh.
it's open.
Oh.
So when you read that set of symbols, that reads as f compose g. It does not read fog. That is Mr. Kulik's gigantic pet peeve. I don't want to hear any kind of fog in this class. We're not talking about weather. That is like an open multiplication dot. Huh? Compose.
So does it mean
No. No fog. We're not talking about the weather. So really, when we talk about composition, what is composition really kind of doing? You're plugging one function inside of another function.
that's quite cool.
So let's do a couple of examples to get used to like how we actually do this composition. Yes.
For the formula, instead of f parentheses g parentheses x parentheses parentheses.
Yes. Yes. All right. So let's just run through a couple of examples to practice how we actually do this composition. Again, this normally would be a review skill, but in our case, I think it's new material. So our first example, we just have f compose g. So using our definition from above, I'm just going to rewrite that as f of g of x. And then I'm going to kind of just work from the inside out. So g of x, we're told, is the same thing as negative 3x plus 4. So in place of the g of x, I'm going to write negative 3x plus 4. Everybody so far so good? Now, when I have something inside of a function like that, what is that really telling us to do?
Multiply.
Not multiply.
Divide.
Not divide.
Hash.
Distribute.
Not distribute. It's telling us to plug that in for x into the function for f, right? If I had f of 3, I'd plug 3 in for all the x's. Everybody agree with that? So let's look at f. F is 2x squared minus 3x. So I'm going to have 2, and then wherever the x is, I'm going to have something squared, minus 3, and then whatever's in place of the x. Did you guys see there?
Mm-hmm.
And what are we dropping into those places?
The numbers.
The negative 3x plus 4. Maybe I'll color code that. Is that okay with everybody?
It's not that hard. Oh, where did the GX go? Oh,
I just used the definition of what g of x is. Right? G of x is negative 3x plus 4. So I replace the g of x with negative 3x plus 4.
so is that just the answer?
Is that just the answer? No, we're not done. The composition part is over,
No, it's
but what should we still have to do? We still have to simplify this, right? So what's the first thing I need to do to simplify this? So PEMDAS, great. So what should I look for first?
Parentheses.
Okay, is there anything I can do inside the parentheses?
No.
Okay, exponents. How do I do negative 3x plus 4 squared?
You have to,
Calculator won't help you because there's a variable
You
in
give
it.
the square to both
Yeah.
variables.
Oh, so you want to write it like this?
no,
No, not like that.
there just be
Actually,
negative 9x plus 16.
actually, it's
Oh,
nice, yeah.
who's the x?
That looks nice.
Is this right?
No.
What I wrote?
I think
No.
so.
No, incorrect. This is wrong. What's wrong with it?
The x is different.
Nope. We never distribute exponents. That is a wrong idea. If I have like 2 squared, what is 2 squared the same as? How did you get 4 though?
I did 2 times 2.
2 times 2, exactly. So negative 3x plus 4 squared should be negative 3x plus 4 times negative 3x plus 4.
2 times 2 plus 4 minus 4.
Right? Everybody agree with that?
So you just get 0.
Everybody agree that's the same thing?
Oh.
And when I have something like this, what should I do? Foil.
Oh.
Oh, I love foil. Inside. Flat.
Oh, I forgot about the
And then
I low-key forgot how to foil.
I'll distribute.
Outside, inside, left.
Yeah. And then we can distribute on the last piece there. I can multiply that negative 3 through. Everybody cool there?
I'm feeling pretty cool, though.
Like I've never heard that one before.
I thought that was pretty original.
Yeah, you can think a lot of things. So everybody okay here?
Yeah.
No. Where did I lose you at? It's okay. All right. And then what do I still have to do still? Distribute the 2 through. Very good.
Oh my god.
Oops.
Hang on, bro.
That's 32.
Why is this
Hang on, 1 second. Oh, yeah.
And now
combined?
I can combine the like terms, right? So negative 48x. Too much side chatter. Negative 48x plus 9x is negative 39x. 32 minus 12 is 20.
Was that the final answer?
That's our final answer. Notice this step, the composition was done. What was really the hard part here? The simplifying, right? The simplifying was all the difficult things. These are all things that we should have been familiar with from Algebra 1. But that's, again, all the hassle there was like, would have been a very hard Algebra 1 problem, because there's a lot of simplifying to do there.
That's just an easy trick problem.
I wouldn't even say it's that much of a trig problem, because it's not really trig. We haven't even really done any trig yet.
It's still pretty cool.
Yeah.
Yeah, it is.
Oh, we flipping it.
All right.
Thanks, bro.
So what if we do G compose f of x? Oh, wait a minute, Mr. Kulik. We just did f compose G,
There's more?
right? Well, it's another example, dude.
I thought it was the same problem.
No, that's why there's a B in front of it. So I can just say it's the same thing, right? What do you guys think?
No.
No, you're right. That's not right.
Because we're gonna have to plug in.
You gotta put the G on the
We
outside.
gotta
We
put
fit
that
it.
down.
Put the F on the inside.
Oh my
No.
god. It's the Zimbabwe guy.
Okay. So we're doing g of f of x. F of x is 2x squared minus 3x. And then if I look at g, that was negative 3x plus 4. And what we're plugging in for x is f of x. So there our composition is now done. What do we still need to do?
Oh, we gotta do that.
Simplify. Now, let's look at the simplifying that we have to do this time.
Oh, it's less.
It's way easier, right?
Yup.
So I just have to distribute that negative 3 through.
That was so easy.
And I'm done.
See, that's what I'm talking about.
Oh. Oh, really? Bro. All you guys are
So the important note that I want to take away from these two examples is that composition is not commutative, that F compose G is not going to be the same thing as G compose F in general. Could it ever be the same?
Yes.
Yes, it could. But is it going to be in general?
No.
No. Sadeki.
Thanks, guys.
Sure, man.
Go enjoy yourself.
All right.
Oh, I will.
Don't take too long, man.
Nah, let's not. All right. So we have this new operation called composition, right?
Yeah.
We can use this now to define something new. So let's say we have two functions, f and g. All right. What's that?
What is if with two F's?
If and only if.
If and.
That's the abbreviation from geometry.
Oh, I knew that.
I think was the last place you probably frequently used the if and only if.
Yeah.
So we say that f and g are two. If f and g are two functions, we call g the inverse function of f. If and only if the composition of f and g is the same as the composition of g and f, both of which simplify down to just x. When this is true, we give g of x a special name. We call it f inverse. So when we read this symbol here, this f with the -1 exponent, we read that as f inverse of x. So what is g of x really doing here? What is an inverse function really doing? It's really undoing whatever the other function did. So let's think about this as a mapping diagram. Okay, so let's say we have some function f that sends 1 to 4, 2 to 5, and 3 to 6. What is its inverse going to look like? Well, first of all, the domain for the inverse needs to be the range for f. So 4, 5, 6. And we need to send 4, 5, 6 back to the domain from f, so 1, 2, 3. And since f sends 1 to 4, f inverse needs to send 4 back to 1. And 5 back to 2, and then 6 back to 3. So what we should see here is that at the end, what have we done?
Flipped.
Nothing at all, right? We sent 1 to 4 and then 4 back to 1. What has changed? Nothing. You're still at 1, right? That's what we want the inverse to do, is just undo whatever the function before it did. So that's what it's going to look like for a mapping diagram. Now, do we do much with mapping diagrams in terms of normal algebra? Not really. It's a nice, like, theoretical way of looking at a function, but practically, like, not very practical. What if instead we have a function that's given by a set of ordered pairs? You okay over there? Yeah, lay off the cigs, my man. Not implying that you're actually smoking. It's good advice regardless, right?
Am I able to wear this at all?
No.
Outerwear.
But if you tucked in your shirt, you might be warmer.
Oh.
It'll help keep the air in. Spend all that body heat warming the air up around you, and it just leaking out the bottom. All right. So here's our function. We define that function as a set of ordered pairs. What is f inverse going to look like there?
It's gonna be the y's are gonna get x.
Yeah, exactly. Now there's a fancy math sounding word for what you just did there. It's called transposing, when you like switch two things. If I go back and I look at these two examples here, does anybody notice anything different about these two examples other than obviously one is a mapping diagram and one is a set of ordered pairs?
No.
Okay, well let me ask you this. If I look at f inverse in my first example, is that a function? Yeah, right? All the x's are used and they all go to exactly one place.
The second one is not because it has 2 8s.
Yeah,
Yep.
That's a royal flush.
excellent.
A royal flush.
I don't think there's any 8s in a royal flush, but okay. And the issue there was that 8 is used twice. So it appears sometimes my inverse will be a function and sometimes it won't be, right? It would be nice to be able to just look at f and be able to tell whether f inverse I should be expecting a function back or not. Everybody kind of agree with that?
I would strongly
Yeah.
agree.
Not the rouge.
Well, the answer here, yes, we can do that. But in order to show this, we need some definitions. Because f has to meet a couple of criteria for this to work. Okay? So let's do some definitions. So we're going to have 3 here, definitions. So function is considered onto if every element in the range can be mapped to by some element in the domain. So what are we really saying there for something that's onto? Is that like all the ranges get used, right? All the y coordinates get used. That's all we're really saying. Everybody okay with that? Okay. Our next definition, we say that a function is considered one-to-one if every element in the domain maps uniquely to one distinct element in the range. So what is one-to-one really saying? The ranges are used exactly once. So range can only be used one time. A y coordinate can be used only one time. And we say if both of these two things happen, we call that function bijective. So, with these definitions, we can now have a theorem. Let's say for a function f, f inverse is also a function if and only if f is bijective. So for a function f inverse is also a function if and only if f is bijective. Let's just see an example of like why we need one-to-one and onto in order to guarantee that f inverse will be a function. Everybody's okay with that? So this is going to kind of substitute in for a proof of this theorem. We're just going to kind of see why we need both of these things. Yeah. So if we look at this function f is f onto. No, why not? Because 5 isn't being used. If we write the inverse for f, what are we going to notice here? Is f inverse a function? No. Why not?
Because not every domain has a
Yeah, not every domain gets used, right? So for f inverse, so if we have a function and all the ranges aren't used, when we make the inverse, those unused ranges become unused domains, which precludes that inverse from being a function. Is everybody okay with that? So that's why we need to have onto to guarantee that f inverse would be a function. Let's look at the one-to-one piece. So here we should observe that f is not one-to-one, right? Because we have a range here that's used more than once. Everybody agree with that? So when I go and construct f inverse, that range that was used more than once is now becoming a domain that's used more than once. And what does that mean? Yeah. So remember, our function definition has two pieces. All the domains need to be used, and they can only go to one place. If my function is onto, that guarantees that its inverse will use all of its domains. And if my function is one-to-one, that guarantees that its inverse will only send those domains to one place. So I need to have both of them to guarantee that f inverse is a function. Everybody's okay with that? Cool. All right. Let's kind of continue now looking at inverses. So we've seen how to write an inverse from a mapping diagram. and we've seen how to write an inverse from a set of ordered pairs. Let's continue. Let's look at how we're going to write an inverse from a graph. Yes, certainly. Okay. So let's say that this is our function, f of x, and we want to draw the function for f inverse. How am I going to go about doing that? What do we know about the x's and y's for the inverse? They switch. So let's start by graphing then 5, -2. -3, 0. And then 1, -1. I'm sorry, -1, 1. Everybody okay with that? Okay. So now I need to connect these somehow. How do I do that, though? So here's the trick. The vertex in F should still be like the vertex in F inverse. So I'm just going to draw starting from -3, 0. So there's that. Did you notice anything about the symmetry of these two functions? This is the line y equals x, and these two are reflections of each other across that line y equals x, right? Like if I look at this part of f inverse, that was this part of f reflected across that line. Certainly. Et cetera, et cetera. Does that see that? So you can think about it either way. You can think about it as a reflection and draw the reflection. I don't like to do that. I think it's easier to just pick some coordinates, flop the coordinates, and sketch a new picture. But either approach is okay. Everybody's okay with that? What do you notice about f inverse, though? It's not a function because it doesn't pass a vertical line test. What part of our theorem did f fail? Because we know if f inverse isn't a function, we know that f couldn't have been bijective. So which part of the bijective failed? Did the one-to-one part fail, the onto part fail, or maybe both? It's the one-to-one part that fails. Why?
Because has multiple.
Yeah, so if I look at, say, this y coordinate here, I notice there's 2 places on my function that have that same y coordinate, right? So yeah, what do we really do here? Is a horizontal line test. What does a horizontal line test do? It checks to see if a function is one-to-one. Yes, Michael.
Is there a diagonal line test?
There's not, to my knowledge.
Could you make one?
I don't know what it'd be showing, but
You should invent that. For like the math guy.
I'll see what I can do in my spare time. Okay. Everybody's still doing okay? At this point, we know how to write an inverse from a mapping diagram, and from a set of ordered pairs, and from a graph. What else do we still need to be able to write an inverse from? An equation, right? So what if we have the function 3x minus 7? And we want to find the inverse. So here's the procedure. Okay? I'm going to solve for x, just like I would if this was a Algebra 1 problem. So that's step 1. So to solve for x, I'm going to start by adding 7 to both sides, right? Little concerning that nobody wanted to answer that, but okay. And then the next thing I would do is divide by 3. And I'm just going to write this as y plus 7 all over 3. So that's step 1. Get y by itself. Or I'm sorry, x. Step 2, we're just going to swap x and y. So instead of calling this y plus 7 over 3, we'll call it x plus 7 over 3 is equal to y. And then the last step would be to replace the y with f inverse. So I claim that x plus 7 over 3 is the inverse to 3x minus 7. Let's check that. The check for this is going back and using our theorem. So the theorem, what we needed to show that two things were inverses was we needed to show that f compose g of x is equal to x and that g compose f of x is equal to x. That's what we're going to show. Let's call this F inverse, right? That'll be a little bit clearer what we're doing. Like, where's the G coming from, Mr. Kulik? Well, you know, like, whatever, F inverse G, Q, 7, they're just names, you know? But, Mr. Kulik, I have a name. All right, fine. The names matter, I guess. Okay. So just like we've done before when we did compositions, look at this all connecting together now, guys. You're like, where was composition going to come back in? Here it is. So when I do F, that's 3x minus 7, and the x in this case is x plus 7 over 3. If I simplify, what do you notice can happen here? The times 3 and divides by 3 can cancel. Good job, Emma. And then what do you notice can happen here? The plus 7 and minus 7 can cancel. And I'm equal to x, which is what I needed. Okay. The other half, I need to show that f inverse of f of x is equal to x. Are you okay with what I did there to the composition? What should I simplify first? There's a right answer here. The minus 7 and the plus 7, right? There's no need for the parenthesis to be there because there's no multiplication going on. Now what can simplify? The times 3 and divides by 3, and we're just equal to x. So these two things are definitely inverses. We have now proven it. I'm just showing you. There'll be questions where I ask you to show two things are inverses. This is how you would do that. If I don't ask you to show, if I just say find the inverse, you don't have to do that. But it's just good examples. All right. The rest of this chapter is just a whole bunch of these examples of like finding the inverses. Let's do one more and then we'll stop for today. We'll have just like a few to do tomorrow before we start, or next time before we start the review, but it's just like one or two examples left that I'd want to do. And it'll be good because this is primarily what you'll be doing in the homeworks also. This is probably the trickiest situation right here that we're going to look at. You like it tricky? Okay. So just like before, I'm going to start by rewriting this with a y equals. And again, the goal is now to get the x by itself. What do you notice here that's different about this problem than the previous ones? You got two x's. Whoa. All right, what should I do first? I would multiply both sides by 5x minus 8 to get rid of the fraction. That's a great first step. Okay. Now what do I want to do? I'm going to get the x pieces on one side and the non-x pieces on the other side. So I'll subtract 2x over and then add 8y over. So now all the x's are on one side and the non-x parts are on the other. Well, I still have x's in two different places. To get x by itself, I have to get x into one place. How can I do that? There's an algebra 1 idea. Oh no. Really, Mr. Kulik? It was so long ago. Do you notice anything in common on that left-hand side? An x, right? What can I do if I have something in common? I can factor it out. You guys see that? And then, what would I want to divide by? 5y minus 2. Oh, Mr. Kulik, that was so sneaky. So now we just swap the x's and y's and rewrite this as f inverse and that'll do her. We'll stop here. Again, I said I have a couple more examples to finish up, which is fine, no big deal. For the homework set, I think last week we had assigned up to 22. Well, I checked for up to 22. You guys could have done up through 30, I think, got assigned. And now we're going to assign 31 up to 51, and then 53 to 56. Nope, 55.
Wait, were we supposed to do 23 to 30?
Not part of the check, but they were problems that were assigned last week, but were not part of the check yet. So they get into this week's. Yes, Mr. Sadecki.
Can I have one of your balloons?
Sure. Okay.
Thank you.
This is all for Sundays. These are all for Sundays. Now these ones it's a lot of problems, more so than usual. And some of these are lengthy. They have lots of parts. So I would get a start early. I wouldn't wait till Sunday. Reminder, next time we're going to finish up these couple more examples and then start with the review stuff. We'll see you next time. Have a great day.